Welcome back, everyone. So in this video, what we're going to do is we're going to be looking at how energy and conservation of energy as well works for objects undergoing simple harmonic motion, being pendulums and springs, the ones we're going to be focusing on the most. I'll start with pendulums, then I'll go to springs. Now, a lot of the ideas between these two things are the same, so when we get to springs, we'll probably be like, oh yeah, remember, boom, 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 same. But there are some specific bits that I will then talk about for each individual scenario. All right, so let's start with a pendulum. Okay, so I drew here just a pendulum at rest in equilibrium. Okay, we know its length right there. And remember, the length is what determines its period. We're not going to talk about period here today, but just want to throw a quick reminder out there. Now, for each point we're going to be looking at, we're going to be seeing how is the gravitational potential energy, kinetic energy, speed, and at times velocity, we'll take direction into account, and acceleration. How are these values affected depending on where this object is in its path? All right, so let's start, since it's here already, with the object in equilibrium. In equilibrium, okay? We're going to say that it's moving now, right? It's just oscillating back and forth. Okay, we're not going to take a look at the pendulum just still because none of these really come into play. It's just a ball hanging on a string. Okay, but it is going to be moving now. This is a whiteboard. It's not Harry Potter land. I can't get it to move. Sorry. Anywho, when it's at equilibrium, right, the height is 0. Remember that for mgh, the gravitational potential energy, that h needs to be based off of some starting point. Well, since this thing's not touching the ground, it's not going to be going to the ground since it's connected by the string, we don't need to measure from the ground. What we'll measure is from the equilibrium point. That's its lowest point. Anywhere up here, it's going to be a little bit higher. Well, if you're at the lowest point, your gravitational potential energy is going to be 0. Awesome. Now, as the pendulum oscillates back and forth, okay, what's happening? Well, as it's going up, it's slowing down. Back the same this way, right? It's speeding up, but then as it starts to go back up, it slows down again. So what that tells you is at equilibrium, the speed is at a maximum. Okay, we're going to go through some tips and tricks to figure out what that speed could be. Now, if your speed is a maximum, that also means that your kinetic energy is at a maximum, right? 1/2 mv squared, mass times speed squared. So if your speed's at a max, your Ke is going to be at a max, your kinetic energy. Now, for a pendulum, this bit's going to become a little bit trickier. Let's talk about the acceleration at equilibrium. Well, horizontally, a sub x, it is 0. Okay, there are no horizontal forces acting on the object when it's at equilibrium. But there are vertical forces, right? If I were to draw a free body diagram for that object, I would see there's a tension force up and a gravity force down. Now, if we were back to where this object was just at rest, no problem. The vertical acceleration would also be 0. But it's swinging, it's moving. Okay? The velocity is pointed horizontally, but we know it's not going to keep moving horizontally, which means your acceleration in the vertical direction is actually a centripetal acceleration. Okay? So, keep that in mind. Yes, it's at equilibrium. That's the point that we call it when it's at its lowest point. But while it's moving, because of the fact that it's staying in this kind of path, it's got a centripetal acceleration. You can sort of look at it as if it's the bottom of a vertical circle, right? Force tension up minus force gravity down equals that centripetal force. Well, centripetal force divided by the mass of the object would be its centripetal acceleration. Right, so horizontally, acceleration is 0. Vertically, the acceleration is that centripetal acceleration. Cool. All right, so that is a pendulum at equilibrium, at its equilibrium point. All right, so what I'm going to do now is I'm going to erase the bits for that. And, erasey. Now we're going to talk about a pendulum that is at its amplitude. It's at its maximum displacement from equilibrium. Okay? Well, if it's its maximum displacement from equilibrium, what that means is your gravitational potential energy is a maximum, right? It says, so if this is my baseline, and this is how high up it goes, right? This height is at a maximum. If the height is a maximum, we say that our gravitational potential energy is at a maximum. Now, in a minute, I'm going to talk about how we can calculate this height, how we calculate this distance right here. Okay? Kinetic energy. Well, when it's at its amplitude is where it's going to stop for a second before coming back and going back to the other end. And the same thing's going to be true on this end. Okay? It stops for that brief instant, which means your speed is 0, which means your kinetic energy is also 0. Okay? Now, acceleration is at a maximum right there. Okay? Even though it's not moving, it's changing direction, right? You can think about a projectile at apogee. Yeah, it stops for that split instant, but it changes direction, so it's still accelerating. There's still an acceleration there. All right, now, let's talk about how we find this height. How do we find how high up it goes? Well, we have to do a little bit of trigonometry, okay? We know this angle. We can measure that angle. They might tell us the angle, whatever it happens, okay? Now, here we have a right triangle, okay? So, if we find this side of the triangle, that is the adjacent side to the angle. Okay, this is our hypotenuse. The hypotenuse is the length of the string. So we can say that from here to here is L cosine theta by just doing the bit of trig. Well, to find this bit, we take the length and subtract it by this L cosine theta. So we take the height, and it becomes L minus L cosine theta. Right? So in calculating your MGH, the H becomes L minus L cosine theta. It's how much ever it was raised from here. So it depends on the length of the string and the angle at which it was raised. Great. So here we have a pendulum at amplitude. Alrighty. Now, real quick, before we move on to springs, I just want to talk about a few things. Well, we know, based on what we just talked about, that at amplitude, the gravitational potential energy is a maximum. And we know at equilibrium, the kinetic energy is at a maximum. Well, this is also a closed system, which means energy is conserved. There's no outside force doing work on the system. All right, so we can say that that maximum potential energy at amplitude equals that kinetic energy at equilibrium. So we can get something like this. Okay, so by using this, we can figure out speed if they gave us a height, or if we were able to find a height. Or we can find height if they gave us a max speed, right? Obviously the masses will cancel out, but you're able to do some calculations here for that, right? This is using conservation of energy for a pendulum. Alrighty, now moving to springs. So I'm going to set up the same basic look. Okay, I'm going to use a horizontal spring as my example. So U, potential energy. I'm not going to use gravitational potential energy this time. I'm going to use elastic potential energy, kinetic energy, speed, and acceleration. Okay. Okay. All right. So here we go. Here we have a box on a spring, and that box has some mass m. Remember, mass and the spring constant helps determine the period of that spring. All right, let's once again take a look at the equilibrium position. Okay, so we'll call that point x equals 0. X equals 0. So there is no displacement there. Well, if x equals 0, right, our elastic potential energy must be 0. 1/2 kx squared. X is 0, that's 0, boom, boom. Okay? For kinetic energy, very similar to a pendulum, right, as it's oscillating back and forth, okay, anytime it starts to stretch away, it's going to slow down. Anytime it starts to get compressed, it's going to slow down. So at equilibrium, its speed is 0, which means its kinetic energy is 0. Okay? And again, just like a pendulum, the acceleration, oh sorry, I did that wrong. Kinetic energy is maximum and speed is maximum at equilibrium, and your acceleration is 0. Sorry. Yeah, so since it's going to be slowing down as it goes beyond, slowing down as it comes this way, your speed is maximum, which means your kinetic energy is maximum, also means your acceleration is 0. This time there is no special acceleration we're going to use here. Right? It's just that. All right, cool. Now let's take a look at the box if it's at some extension, right? So it's hard to draw, so I'm just not going to put it there, but we're going to pretend like it's way out here. It's been stretched a bit at its amplitude. Okay, so how does that affect these values? Alrighty. Well, if it's at its maximum displacement, that x is at a maximum, which means 1/2 kx squared will be at a maximum. So we have your elastic potential energy as a maximum. Okay. Just like a pendulum, when it's at its end, it's stopping for an instant and turning around. Same thing over here. So your speed and kinetic energy are both 0. All right, and your acceleration will be a maximum. Cool. So, one thing I do want to take a kind of quick step aside before we finish up here is how do we calculate that acceleration for a spring? Well, we have to use something called Hooke's law. Hooke's law says that the force bringing an object back to equilibrium is directly proportional to its displacement. So force equals spring constant times that displacement. Okay. Now, technically speaking, there should be a negative sign here, right? Because the force is going to be in the opposite direction of its displacement. So if it's way out here and positive, the force wants to pull it back negative. I often drop that off. Just know that when it's out here with a positive x, if we're calling this positive, the force is directed back this way. It's got a negative direction to it. Anyways, back to this. So we have our Hooke's law, which says that the force acting on the object when it's stretched out someplace is dependent on how far it's stretched out. Well, if it's out here and there's no friction or anything like that, we'll say that that spring force is the only force acting on it, which makes it its net force, which we then can say equals ma. So we can calculate our acceleration by knowing the mass, displacement, and spring constant of that object. All right, so that is how we would end up using something like this. Awesome. Now, just like with a pendulum, I'm going to talk about using conservation of energy to help solve for whatever you may need to solve, right? Well, we're going to have 1/2 kx squared at its maximum elastic potential energy at its amplitude will equal the kinetic energy where it's at its maximum in equilibrium. Right? 1/2 will cancel out. We can use any of these other values to solve for any of these other values. All right, so that is pretty much energy of an oscillator, spring, pendulum in a nutshell. All right, I really hope that was helpful. Let me know if it wasn't. Cowabunga.